Spurti, Arshita, please go ahead.
Sir.
Please take some snapshot also. Spurti or Arshita, you take some snaps.
Sure, sir.
Yes, sir.
A very good evening to one and all present here. IEEE Mysore subsection with IEEE Bangalore section, IEEE Information Theory Society Bangalore chapter and IEEE Circuits and Systems Society Bangalore chapter is organizing its fifth webinar on supervised pattern classification with Optimum-Path forest. I, Spurti B, from the Department of Electronics and Communication Engineering on behalf of GSSS Institute of Engineering and Technology for Women, Mysore, take this opportunity to tell a few words about IEEE Mysore subsection. IEEE Mysore subsection, established in the year 2020, is one among the three subsections of IEEE Bangalore section. The objective of IEEE Mysore subsection is to conduct various student and professional activities like invited talks, student internship, workshop, flagship conferences. IEEE student branches of Mysore, Mandya, Hassan, Chamarajnagar, and Kodagu districts come under IEEE Mysore subsection. Currently, the subsection has more than 1,000 IEEE members and around 15 IEEE student branches. The subsection aims at enhancing professional networking and promoting humanitarian activities. IEEE Mysore subsection was inaugurated by Ms. Susan K. Land, IEEE President, USA 2021 on 21st December 2020 and delivered the inaugural address. It's honor for me to welcome our today's speaker, Dr. João Paulo Papa, Chair, IEEE BIKM Task Force, Professor, São Paulo State University, Brazil, to enlighten us with his knowledge. A hearty welcome to you, sir. I would like to extend my hearty welcome to Dr. Parameshwachari BD, Professor and Head of the Department of Telecommunication Engineering, Chair IEEE Mysore Subsection and Chair IEEE ITS Bangalore Chapter. Welcome you, sir.
Thank you.
I would also like to welcome Dr. Deepa Shanai, Chair IEEE Bangalore Section and Professor UVCE Bangalore. A hearty welcome to you, ma'am. I would like to welcome Dr. Chalaja S., Chair, IEEE CAS Bangalore Chapter, Associate Dean, BIT Bangalore. Welcome you, ma'am. I also welcome office bearers and the EXCOM members of IEEE Mysore Subsection, IEEE Bangalore Section, IEEE Information Theory Society Bangalore Chapter, IEEE Circuits and Systems Society Bangalore Chapter. I would also like to welcome participants of today's webinar. I would also like to welcome all the IEEE staff and student coordinators for their support. I welcome all my fellow students and friends. Once again, welcome each one of you present here. Now, I request Sri Arshita P. to take over the session and introduce our today's speaker, Dr. João Paulo Papa.
A very good evening to one and all present here. I am Sri Harshita P. from the Department of Electronics and Communication Engineering on behalf of GSSS Institute of Engineering and Technology for Women, Mysore. Take this opportunity to introduce our today's speaker, João Paulo Papa sir. Dr. João Paulo Papa received his BSc in Information System from the São Paulo State University, Brazil in 2005. He received his MSc in Computer Science from the Federal University of São Carlos, Brazil. In 2008, he received his PhD in Computer Science from the University of Campinas, Brazil. During 2008 to 2009, he had worked as a postdoctorate researcher at the same institute. And during 2014 to 2015, he worked as a visiting scholar at Harvard University. He has been a professor at the Computer Science Department, São Paulo State University since 2009, and his research interests include machine learning, pattern recognition, and image processing. He is also the recipient of the Alexander von Humboldt Fellowship and the Brazilian representative of the International Association for Pattern Recognition. It's an honor to have you with us, sir. I request all the participants to put their queries in the chat box, which will be answered at the end of the session. Now I request João Paulo sir to take over the session.
Thank you all for the invitation. Thank you all the students, all senior members, professors, and a special thanks to Professor Paramesh Hadi. I hope I spelled your name correctly, for the invitation. So it's a pleasure to be here. I think these kind of meetings are very important to get people together and, you know, share some knowledge and expand our network. So I'm from São Paulo State University, as I have been presented. And I work with the School of Science, Department of Computing. Today, I'm going to talk about pattern classification, actually supervised pattern classification with Optimum-Path forest. I'm not going to talk about deep learning. That's basically, I'm going to show you this technique that's called the Optimum-Path forest. It's based on graphs. And then for sure, we can use it together with deep learning techniques. We have tried it before with good results. And I think it can be some sort of inspiration for you guys, even for the beginners and the most senior members, right? So maybe I'm gonna say something that's quite well known for you guys. So my apologies, but I have to do some sort of introduction here. Maybe some of you don't know this kind of thing, but let's do it. So I'm gonna just give you a brief introduction about the topic, just 1 or 3 slides, and then I'm gonna show you the Optimum-Path forest classifier, and then some applications in remote sensing. It's just like one application I pick it, and then I'm gonna talk about the recent work we have done concerning data augmentation, which I think it's kind of important nowadays, maybe because of deep learning, and some future works. Okay, if the sound is not good or something, I'll just let me know, okay? I got a flu a few days ago, so my voice is not that much good. So my apologies. So basically, as we know, the pattern recognition, it's a very standard problem. And we know that basically we need to find a function, right, that can partition the data in different classes in given a feature space. I'm talking about supervised classification here, okay? And then we know that we have this kind of thing here, and the main idea is to partition. I mean, is to divide the feature space. We have like here I have an example of a 2-class classification problem. I'm trying to distinguish between, let's say, cars from beaches and this kind of thing. And then we're gonna, we extract features and we have points here, and then we're gonna somehow separate, and we can do that explicitly. I mean, we're gonna try to find a decision boundary like neural networks or support vector machines. They do find the parameters of that hyperplane, for instance. Okay. We also have approaches that again try to separate the space, but they don't use any kind of boundary explicitly, like KNN or even OPF, as you're gonna see, right? That's the main thing. And some of my students, they ask me, so what's the difference, right, between machine learning and pattern recognition and artificial intelligence? And I usually I used to say them, just not to worry about that. That's to my viewpoint, there's no very much clear difference between all this kind of thing. It really depends on the technique you are using to work, depending on your age. Have some friends that are older than me, and they say they do work with artificial intelligence. They don't work with machine learning, but they use neural networks and this kind of thing. So it's just a matter of, you know, different viewpoints. It's just like some curiosity I like to show you. Just don't bother with this matter here, right? So usually I say machine learning or pattern recognition or artificial intelligence, but it's all the same thing to me, right? It really depends on the audience. If I'm gonna talk to some journalists, I'm gonna say, okay, I work with artificial intelligence. I'm not gonna say I work with pattern recognition, right? So, okay, that's the brief introduction. As I said, probably most of you guys, you already knew all these kind of things, because that's the basics of machine learning. So, and then I'm gonna show you. I'm gonna talk about the Optimum-Path forest. That's the main thing here. Right. So there is a collection of techniques that are based on graph theory, right? Graph theory, probably you know that as well. It's a, let's say it's a field of computer science, basically, that studies how can we model some problem using nodes and edges, arcs. How can we connect them, and then how can we solve problems in these graphs, right? And the same thing can be applied to pattern recognition, right? So the OPF, the Optimum-Path forest, is not only one classifier. Okay, I'd like to make that clear. The OPF, it's a framework. I'm gonna explain that a little bit later. By framework, I mean, imagine you are going to a supermarket, and then you have some pieces of OPF you can buy for free, right? Which is good. And then you can design, you can assemble your own OPF, right? So that's a framework. You can create, you can come up with an OPF that works specifically for your problem. So you have a new OPF classifier, right? So basically, what's the main idea is to have, let's say, it's a competition process among prototypes. I'm going to talk about it. I have a picture to show you. So remember Dijkstra? Probably you know Dijkstra algorithm, right? So we have a source node, and the main idea of Dijkstra is to compute the minimum distance.
Dijkstra's algorithm ಬಗ್ಗೆ ಹೇಳಕತ್ತೀನಿ.
Yes, Dijkstra. So given a source node, right? Basically, the main idea is to compute the minimum distances between this source node to all other nodes of the graph, right? We can do that. Let's say I have 20 cities. Each city is going to be a node. And given an initial city, the source city, I'm going to compute the let's say the shortest paths from this city number one to all other cities. So basically, the OPF, we can understand it as a generalization of Dijkstra. I'm going to show that, right? So it's basically the main idea of Dijkstra. Suppose we, instead of having like only one source node, we have several source nodes, and then we'll try these guys. They're going to try to compete among them, right? They're going to try to fight among them, conquer other nodes. And by conquering, I mean try to offer better costs, and also together with the costs, we have the labels. Okay, and we're going to explain that later. So basically, as I said, you can design your own OBF classifier, and to do that, you have to choose 3 items from our supermarket, right? So we have adjacency relation, because to define a graph, we need the nodes and the vertex, and the edge, the arcs, and the vertices. We have a methodology to estimate prototypes. Remember, the prototypes, they're gonna be the nodes that start the competition, and they're gonna, they're gonna try to fight, conquer, in order to conquer other nodes. That's the thing. There is different ways to find them, and we're gonna show you one heuristic here. And then finally, remember, these guys, they're gonna try to offer some sort of reward to the other nodes in order to try to conquer them, right? And this reward is going to be a function value, right? We call that the path cost function. So basically, the main idea, the general idea of the OPF is, so I have a training set. Let's say, suppose I have a training set with 2 classes. I'm going to find 2 prototypes, one prototype for class 1 and the other prototype from class 2, right? And these guys are going to start the competition process. That's basically an optimization problem. What is the optimization problem? Each prototype is going to try to offer the smallest cost to all other samples. And in the end of the process, we have some training samples that have been conquered by one prototype from class 1, let's say, and the remaining samples have been conquered by the prototype of class number 2. And then we have the graph has been partitioned in this kind of toy example in 2 subgraphs. And then we did the partition, we did the classification here, right? And we have a question here from Dimple. OPF is pretty supervised learning based, as you said, for this literary. Yeah, yes. In this sense, for the first question here, if you don't mind, I can answer questions. Some slides later, but the OPF, we have supervised versions, unsupervised, semi-supervised versions. Basically, we have any kind of scenario with OPF. Okay, we're going to talk about the supervised version only. Okay, right. So as I said, we can create a new OPF classifier by just changing either adjacency relation, methodology to estimate prototypes, and the path cost function. I have some things that here I think it's more interesting for you. Just some examples here. As I said, currently we have 2 main supervised versions. The one that uses a complete graph, that's the one I'm gonna show you today, right? The other uses a KNN graph, the K nearest neighbors graph. We have an unsupervised version. That probably is gonna answer Dimple question. And we have a version. These are good references. We have more recent ones, but I just decided to show you the main references about these techniques. Okay, the first ones, let's say, right? This one in the main publication of OPF that's being published in pattern recognition. Just a curiosity, we have been awarded as the most cited paper in pattern recognition in 2012 with the OPF classifier, which is good. So as I said, so basically the primary idea is to model the problem as a graph partition. How can we do that, guys? So we have the data set, okay, and it's pretty standard approach. We have the data set here. We're going to extract feature vectors, right? You can extract anything. You can use, I don't know, handicraft features. You can use deep learning, whatever. And then now, as I said, a graph. To build a graph, we need the nodes and we need the vertices. So each, this is going to be clear in soon. So for each feature vector is going to be a node of the graph, right? We need to, and we are going to connect these samples, these nodes, with arcs, edges, right? These guys, the nodes and arcs, can be weighted. Let's say I have like Dijkstra. We have some cities around my hometown, and I'm gonna say, okay, each city is gonna be a node, and if we have like a road between cities A and B, I'm gonna connect them in the graph with an edge, with an arc, and I'm gonna weight this arc, right? In this example, the weight of the arc weight is gonna be the distance between these two cities, for instance. A pretty standard example, right? But also the nodes can be weighted, right? In the supervised version of the OPF, we also weight the nodes, which is interesting, right? I'm not gonna get into details about the weighting nodes, but when I'm gonna talk about data augmentation, I'm gonna say something about it. Okay, that's okay. So if you have any questions, you can just type or ask, right? I'm not listening very well because of my flu, but I'm gonna try to do my best. Sorry. So as I said, we have different versions of OPF. Today I'm gonna show you the first one, and I think that it's probably the most used one actually. Right. Remember, we have to choose three items, as I said here from our, let's say, supermarket. The first one is the adjacency relation. Okay, how we are going to connect the nodes, right? We can either use, for instance, a complete graph. What is a complete graph? It's a graph where every node is connected, right? We have an arc connecting every node, so every pair of node is connected. You can ask, oh, but I'm gonna have to use a lot of memory to store all these adjacency relation, but actually you don't need any here to store the arcs because it's connected to everyone, right? Every node. How are we going to estimate the prototypes? That's a good question, right? We actually, to be honest, we started with a random sampling, which is a simple one. It doesn't work well. I'm going to show you in the next example here. And then I'm going to explain to you, I think it's better to explain to you guys why we use the minimum spanning tree in a figure I have next. I think next or in the next slide. Right. So basically the methodology to estimate, right? Is a question or okay. So and then the path cost function we're going to use here, we call it X. Again, this is going to be clear in the figure. Probably, yes, that's the figure. And we're gonna, all these things, guys, is going to be way more clearer here in this figure, okay? So let's get started. Right. So basically, as any pattern recognition technique, we have a training step and a testing step, as an inference step, as you know. And what is the OPF with complete graph, right? Training step. So let's start with this graph here, right? The first one here, the leftmost one on the top. So we have, let's say we have a training set with two classes, right? We have the green and the purple. Here, B and C belong to class, the green class, D and E, they belong to the purple, right? So the main idea is to somehow learn from this graph and then say, okay, I'm gonna try to partition the graph so that green samples, they're gonna stay from one side, and the purple samples, they're gonna belong to another cluster. That's okay? Right. So the first thing we're gonna do is to weight the arcs, remember? Here, so the arcs are weighted. I gave an example A simple way it could be the distance between two cities, but here we have feature vectors. So a good thing of an OPF is how are we going to weight the edges? We can use several things. The most basic thing is just to compute, let's say, the Euclidean distances between the feature vectors of all these samples, right? It's pretty standard. So these are just like, they are not real examples, but kind of not that random too. But so basically here we can compute the Euclidean distance between feature vectors, so we can have the distance among all graph nodes, right? That's okay. A good point here, guys, with OPF is that in situations you have feature vectors with different dimensions, right? Let's say you're gonna try to extract minutiae from fingerprints, and for sure you may have a different number of minutiae for each fingerprint. Can use some kind of bag of visual words to standardize that. But if you don't want to use a bag of visual words, you can also you can use graph nodes with different dimensions. But now instead of, and the next question is, how are you going to compute the distance between these nodes, right? You can use a matching function, right? So that's a good thing with OPF. If you have feature vectors with the same dimensions, that is a situation that happens mostly, right? Okay, you can use Euclidean distance, you can use Manhattan distance, you can use anything, any similarity function, dissimilarity function, but also you can use matching functions here when you have feature vectors with different dimensions, right? Good. So for a thing, we have a adjacency relation, and then we compute the distances. So we have a weighted graph. So remember, guys, the next step is we need to choose the competition, right? And for that purpose, we need to estimate, we need to find the strongest guys. We call them the prototypes, right? Let's say it's a kind of similar to support vectors in support vector machines, in the sense that they're the basis to build a hyperplane in the thing, right? But we're not going to build a hyperplane here, but we can do some sort of analogy here. So in this example, guys, as I have two classes, okay, I need at least two prototypes, okay? One for each class, because we need a representative for the green class, and we need a representative for the purple class, right? If I only one representative, the other class is not gonna be represented, okay? In this example here is a kind of toy example. We have two classes, and we're gonna find two prototypes, okay? So the question is, how are we going to find them? Right. If I had a neural network, guys, let's say MLP network, and if I was looking forward to find a hyperplane to separate samples from different classes, okay, probably, I don't know if you can see my cursor here, but probably I'm gonna, like learn a hyperplane here, more or less in this region here, right? I hope you can see my cursor here. So basically, we are looking for, we are going to try to place prototypes in the boundary class, right? Because the boundary of the class is there. Is in there we have the problems, right? Because we have elements from different classes that are kind of usually close to each other, and there we're going to have misclassification, right? So we are looking to protect these region actually. And in a graph, how are you going to find the closest elements, the closest nodes, but with different classes? We can try to compute the distance among all nodes, and we can do that, but it's going to be like a cubic complexity. We can easily solve that by just computing the minimum spanning tree. Remember? So the minimum spanning tree is red path here, right? The minimum spanning tree is it is a subgraph, right? That covers all nodes of the former graph, the black graph, right? It connects all nodes, but the summation of the arc weights in this path is the smallest as possible. That's the minimum spanning tree, right? Probably you also learned that, right? If you got some graph theory class or something. So basically, the minimum spanning tree is this path here in red. Okay, guys? Right. So as you can see, if I take a walk here in this path, in some time, I'm gonna cross, let's say, this boundary here. What is that boundary? It's an arc, it's an edge that connects two elements from different classes, right? So these two guys here, this guy, they're going to become the prototypes, okay? So A and D, I'm going to just mark them as in this dashed circle here. These guys are going to be the prototypes. That's so when I say I'm going to use the MST to find prototypes, that's the thing, that's the way we do, right? So we're going to just elect the prototypes as the nearest samples from different classes. Okay, these guys are going to be the prototypes. And now we can start the competition process, right? That's okay. If I have any question, guys, you can just type. I have also, if you go to YouTube, and if you type Optimum-Path forest, lecture, one in Portuguese and another in English, by myself about OPF. I think it's way more detailed there. If you want to learn a bit more about OPF, you are free to go to YouTube and watch that thing. And also you can send some email later. You can drop some email for me. So and then okay, we have the prototypes here. As I said, we have now the competition process is basically an optimization process. What is the meaning of that? So basically, we are going to offer, the prototypes are going to offer the smallest cost to all SAM training nodes. Okay, let's say, as you can see here, we have 0 cost for prototype A and Z. Okay, 0. We're gonna analyze the algorithm here. All other nodes, they're gonna have a very large cost, right? Plus infinite here. Okay, so the OPF only works with arcs that are positive valued. Okay, if we have arcs with negative values, the OPF is not gonna work. Okay, but usually we don't have this kind of situation. So basically, we're gonna put all these nodes in a priority query. Okay, and I'm going to remove the nodes with the smallest cost first, right? So if we put all these nodes in a priority query, for sure, either prototype A or D, they're going to come out first, right? Because they have the 0 cost. All other plus infinity. Let's say we got the node A first, right? So now that's the thing. Node A is gonna try to conquer all these neighbors, all its neighbors, right? So let's start. Okay, what's gonna be the? Remember when I said here, I'm using the path cost function. So now we know what is a complete graph. We know what is a minimum spanning tree to find the nearest samples from different classes. And now I'm gonna explain you about the path cost function, right? A common path cost function, that is the one Dijkstra uses, That's basically the summation of the arc weights, right? If it, let's say, if I'm planning to go from city A to city C and I need to pass through city B, right? I need just to sum the arc weights. It's basically the total sum I'm gonna drive or I'm gonna walk, right? And Umerabanu asked how to calculate the cost of a node. It's a good question. And then that's what I'm gonna talk about now. So remember, we just initialize all nodes with plus infinity, except the prototypes. They start with 0, right? Okay, let's go. We just remove node A. No, let's say we're gonna remove node A first. And then node A is gonna try to conquer node B, node C, node E, and node D. Well, one per iteration. So what's the cost that node A is gonna offer to node B? F max. What's the F max? Is the maximum value, right, between the cost I have. So I'm the node A. Okay, I'm gonna try to conquer node B. I'm gonna say node B. I'm gonna offer cost dot 3. Okay, why dot 3? Because the maximum value between 0 and dot 3. And B for sure, B is gonna accept that because B has plus infinite cost, right? So the cost to B is gonna be dot 3. I'm not sure it's clear, Umera Banu or not. And then node A has conquered node B, okay, which means that node A is gonna label node B with the green color, right? And then we're gonna have an arc, a directed edge. That's basically an edge with an arc pointing from B to A, like this one here. But we're just here first, right? We're gonna just, we have this arc here that's gonna say, okay, B has been conquered by A. That's because we have this directed edge here, and B has the cost dot 3, right? Let's go to the other nodes. So what's the cost that A is gonna offer to C, right? That's basically the maximum value between 0 and dot 5, okay, is going to be dot 5. So C is going to for sure accept dot 5 because C has plus infinity. So the cost of dot C by now is going to be dot 5. And C has been conquered by A. That's okay? A is going to try to conquer node E. That's from another class, but don't worry about that. And now to offer 1.9, right? That's the maximum between 0 and 1.9. For sure, E is going to accept it because E has plus infinity. So E has been conquered by A with the green label. I don't have this step by step here, but just to show. And then A is going to try to conquer the other prototype, but a prototype cannot conquer another one, right? It's impossible because, as I said, we don't have arcs with negative values, okay? And there's no way to have a cost better than 0, right? And then D, okay, A has tried to conquer anyone here, so he comes out of the play, and the next node of the priority query is gonna come out. That's gonna be node D, and the node D is gonna do the same thing. Try the node A, it's not gonna work. It's gonna try to conquer node B with 1.2, but it's not gonna work. We have dot 3. It's gonna try to conquer node C with 1.2. It's not gonna work, but it's gonna try to conquer node E with dot 3. That's gonna work because E was conquered previously by node A with 1.9, and dot 3 for sure is better than 1.9. So D reconquered E, right? And then now the next node to come out of the queue is going to be node B. Node B is going to try to do the same thing, but the most important thing here is that node B offered, remember that node C got the cost .5 from node A, the first some iterations ago, but now B has offered the cost .4 to node C, which is way better than .5. So that's because we have here the final, and guys, we have a configuration here. That's that in terms of graph theory, we have a tree here, a tree, the green tree. A tree is a graph with no cycles. It's a connected graph with no cycles. We have two trees here and a collection of trees. That's basically a forest, right? Which is true in nature. So but we have more than that. This is an optimum path tree. It's a tree that encodes the optimum paths. That means that C got the cost .4 only because it has been conquered by B. We can see that by this edge here. And C has been conquered by node A, that's prototype. We have a very strong connection here, right? That's an optimum path. So OPF uses the optimum path connectivity among samples. It's stronger than using just distances, right? So in the end, we have an optimum path forest. That gives the name to the classifier, okay? And the inference, the testing phase is kind of straightforward. We have the optimum path tree generated in the first step, and you're gonna have a new node here to be classified. Let's say node X, and you're gonna compute the distance between X and all of the other nodes. And again, A is gonna offer the max between 0 and .4. B is gonna offer the max between 0.3 and .5, and so on and so on. And you're gonna take the minimum, the smallest value of all these max, and X has been conquered by E, right? That's the final classification, okay? Right, we have some examples, okay, in remote sensing, for instance. We have some examples for satellite image classification. Here we're gonna try to classify crops, coffee crops, roads, bare soil, and the thing. Just some examples of previous works. We have all these data, guys, available for free if you wanna use these things, okay? They are pixel labeled, very good images. We have the standard OPF versus SCVM, and here we have OPF a bit better with Markov random fields. You can see results are better than SCVM. Currently, we have OPF for multi-label classification, video summarization, image retrieval. We have a version in CUDA. We have a dlib OPF, guys, actually. It's written in C language, and also in Python, if you want to use the OPF in Python, right? We have also the OPF in R. We also have an unofficial version of OPF in MATLAB too, right? All these things are freely available if you wanna use. And finally, just to finish here, that's a problem we have been working recently. That's basically, we know that unbalanced data sets, they are a big issue in any pattern recognition problem, particularly in medical applications, right? Usually we have more health people than people with disease sometimes, or sometimes we have the other way around. We have more patients, people with disease, than healthy people, because usually healthy people, they don't go to the hospitals, right? We only have examples from some people's disease, and we gotta try to work on that using oversampling or undersampling, right? Basically, oversampling, I'm going to take the minority class. Suppose I have a two-class classification problem, and for oversampling, I'm going to take the minority class. Let's say you have a class with a lot of samples here, and a class with less samples here. And by oversampling, I'm going to take the minority class and create artificial samples so that they can be more or less the same size. And undersampling, I'm going to do the other way around. I'm going to just decrease, I'm going to remove samples from the majority class so that they can have more or less the same size. So, but the question is, I cannot remove any kind of sample at random because it can. The problem is if I remove some important sample, it's going to degrade my classifier's performance, right? And usually for high resolution imaging, you know that GANs are awesome for synthesized images, right? We know they have some problems, mode collapse and some things during training, but they're awesome. But when we use like low resolution data, by low resolution data, guys, I mean ready-crafted features, okay? Like some hundreds or dozens of features, not the whole image with millions of pixels, right? One of the most standard approaches, probably you are aware of that, is the SMOTE, and we have a lot of variants of SMOTE too, right? And then recently proposed the oversampling via OPF. We call it the O2BF. That's basically we use unsupervised OPF. The one I did not mention today, I used it unsupervised OPF to cluster the sorry, my son is on my background. We have the samples. We're going to cluster. So imagine we have clusters in the feature space. And the good point is that in supervised OPF, it does not require the number of clusters beforehand, like k-means, for instance. Okay, OPF, we say that OPF computes on the fly, like it's going to discover the number of samples, right? And, sorry, clusters. And then basically, I'm going to cluster all samples. And for each cluster, I'm going to try to estimate a Gaussian distribution, right? And then when I'm trying to create new samples, I'm going to create new samples in the smallest clusters, right? Using that Gaussian distribution. So each cluster have a Gaussian distribution. Here, just an example, right? There was publishing this work here for breast cancer. So basically, we have benign samples, the red ones, and malignant samples, the blue ones. And we tried to increase the number of blue samples, the malignant, and the green crosses are the artificial samples generated by O2PF, right? As you can see, we just generated samples in the region of the blue area, right? That's the minority class. Just some examples. We have a new paper published, actually, I think it's going to be a month. Here. We working on 18 data set against 14 state-of-the-art techniques, and OPF and O2PF outperformed all these techniques in all scenarios. So we were very, confident in that result. For future works, we are going with domain adaptation, integration with deep learning. Actually, if you just replace the softmax function with an OPF, for instance, you can get very nice results. Some guys, they do that with SVM. It's few-shot learning with classification. And we have recently published a book about the Optimum-Path forest. If you are interested, I can also send you some samples. In this book, we have, the very basic theory. We have a survey about OPF. OPF has been, evaluated in more than 100 different applications, and I think it's nice to but also you are always welcome to propose something different. So that's it. I really thank you for that opportunity. I'm very happy to be here. I have 2 or 3 friends from India that we are collaborating together. So I'm very happy to be here again. Thank you so much. If you have questions or no. Or you can type the question here if you are too shy to ask. But I invite you to to have a look at the YouTube channel if you want to know a bit more about OPF. That is
Professor Kulkarni, I'm chair-elect for the IEEE Mysore subsection.
I'm sorry?
Yeah, myself chair-elect for the IEEE Mysore subsection.
Oh, right.
Yeah, just a small question. So what's the similarity or the difference with the random forest algorithm?
Oh, right. Well, to be honest, they're completely different. I mean, I think the only similarity is that they use graphs. That's the only thing. But it's a good question actually, because a lot of people they asked me about that, right? The way we handle the competition problem, that's the different thing. If I may, there are two questions here. One is from Su. Can we classify? We can classify anything that can be classified, right? We worked with image classification. We worked with signal classification, EEG, electroencephalogram classification, music, genre classification, right? In real-time applications, we have some examples for intrusion detection in computer networks, okay? That can very nice for real-time applications. And also medical image segmentation or medical image classification, right? And then you have like the physician, is gonna, let's say, mark some parts of the images and they're gonna classify. We also let's say this, the physician is going to mark positive, try to do brain classification, gray matter. The physician is going to mark the gray matter and the white matter, and then we're going to train with that samples and classify the image. This is needs to be fast, right? The physician is not going to wait like half an hour, have a coffee, lunch, and come back. And then suppose we have the image classified, right? But the physician, he or she wants to correct some minor mistakes. Is gonna, mark a few more samples here and another there. And the good point is that the OPF does not need to be retraining again from the scratch, right? We just published in the last year, we called an incremental OPF that basically we keep the knowledge from the previous training. We're gonna add training, but we're gonna do some sort of training that's gonna work only in this new region, okay? There is no need to train the whole thing again. And we show that we can obtain not the same, but a very close, similar solution, right? Yes, OPF can be applied for ECG. I think we do have a work on ECG as well, right? In the past. Can we use OPF for training a neural network? Well, to be honest, it's a good question. We have a work published in 2014, I guess, if I'm not mistaken, where we find better initializations, better parameters for a neural network with radial basis function. And also we submitted a paper to ICPR, which we find better initial locations for the centers of concerning the Gaussian mixture models, the GMM. So we can use these to try to help neural networks too. OPF for retinal image classification. I think we did a work 2 or 3 years ago. We got interesting results too, but for sure we need to explore that more. But I think we did a work on retinal image with OPF too, with some friends, actually, with some friends from India, but they were working in Australia in that time, right? So more questions. There is one from so if you can, OPF can be applied in heptagon environment from Sunil. But I'm sorry, Sunil, I don't know. The heptagon is a kind of it's a kind of framework or backend or something. I have never worked with heptagon. I don't know that one. And here I have our homepage, right? Recogna.tech. If you are interested, we have source codes, we have data sets there, information about our group. You are free to have a look there, right? No more questions. Oh, any book related for image processing? Oh yes. That book I mentioned here, we have a chapter, one or two chapter. They applied OPF for image processing. Also, there is another technique from my PhD supervisor a decade ago. That's basically the same thing, but at that time, the name was not OPF. The name was image forestry transfer, right? IFT, that's the same thing. But basically, IFT is a kind of OPF related to image processing. You can perform image filtering. You can do mathematical morphology with OPF. You can do skeletonization, right? A lot of things. So yes, we can work with this kind of segmentation, image segmentation, right? And Su has asked what I'm currently using OPF for. So our most recent work was that one for undersampling and oversampling. We just finished and we submitted a work to ICPR, International Conference on Pattern Recognition, where we enhanced the initialization of the Gaussian mixture models, GMMs, with OPF. So now I'm also trying to fit OPF in collaborative filtering, right? I have a PhD student is working with recommendation, and now we're trying to put OPF in recommendation too, and basically mix with deep learning. There is no way to move away from deep learning too, right? No more questions. So right, I think that's it. I think we head into 11:30, right? If I'm not mistaken. I thank you guys for the invitation. I'm really glad to talk about OPF. Due to the pandemics, it has been quite a while. I have not been traveling anymore, but hopefully we can also meet someplace. Software. Well, regarding OPF, I started with the libOPF. I implemented the libOPF in C, right? actually, I'm from the old school. I prefer C than Python, but you know, everyone uses Python today. And my student, Gustavo, he's at Microsoft Research now. He implemented the, I think you're gonna like that more than libopf, the OPPython, this one here. I'm gonna send that presentation to you guys, so you can have a look at that, and also you can have a look at the
Hey, wherever
the links to.
వాకిరా ముందు మాట్లాడుతున్నావా వేరే కూర్చుంది
Here. Okay, guys, anything else? So,
Thank you, sir. It was such
these
a
are the links,
thoughtful
okay?
webinar.
Thank you.
Yeah, it was such a thoughtful webinar, sir. I hope the knowledge gained by this webinar would be fruitful to the young minds present here. As we have come to the end of the webinar, I request Sri Harshita P to render the vote of thanks.
It was a great webinar, sir. As we have come to the end of the webinar, I'd like to extend my heartfelt thanks to Dr. João Paulo Papa, sir, for the great information. Thank you, sir. I'd like to
Thank
thank
you.
Dr. Deepa Shanoy, Chair, IEEE Bangalore Section, and Professor, UVCE Bangalore. Thank you, ma'am. I'd like to thank Dr. Parmesh Acharya BD, Professor and Head of the Department of Telecommunication Engineering, Chair, IEEE Mysore Subsection, and IEEE Student Branch Counselor, GSSS IETW, Mysore, for constant support. Thank you, sir. I'd like to thank Dr. Jalaja S., Chair, IEEE CAS Bangalore Chapter, Associate Dean, BIT Bangalore. Thank you, ma'am. I thank all office bearers and execom members of IEEE Mysore Subsection, IEEE Bangalore Section, IEEE Information Theory Society Bangalore Chapter, IEEE Circuits and System Society Bangalore Chapter for conducting this webinar and support. And I once again thank all those who are present and making the webinar successful. Thank you.
Thank you so much.
Thank you all. Have a
Have a
great
good evening. Bye-bye.
Okay, thank you, sir.
Thank you.